Hello everyone, this is Colin from Fiber Optics for Sale. In this video, I will explain what is chromatic dispersion. So let's get started. So what exactly is chromatic dispersion? Let's take a look at this picture. In an optical fiber, different colors of light travels at different speed. The blue light may run faster and the red light may run slower, as represented by the blue color car and the red color car in this picture. Even though they start at the same time in the beginning, they arrive at the destination at different times. This time delay is called chromatic dispersion. Here, chromatic stresses the fact that the time delay depends on the color difference or wavelength difference between the lights. So what effect does chromatic dispersion have on fiber optic communication systems? The direct effect is light pulse broadening. A perfect light pulse starts at the beginning. After it travels a length of fiber, may it be 100 meters or 2,000 meters, the light pulse becomes wider than the original signal. This is caused by chromatic dispersion, because in the same pulse, the blue light travels faster and the red light travels slower, so the total width of the pulse gets stretched wider. Now let's look at the bottom part of the picture. Two perfect signals start at the beginning, but at the end, since both pulses get wider because of chromatic dispersion, they get overlapped to each other. If the overlap is too big, the detector may not be able to recognize these two signals, and you get an error. So chromatic dispersion causes pulse broadening and bit error. Chromatic dispersion is actually the sum of two different dispersion types. The first type is called material dispersion. This is because that the refractive index of silica, the material used to make optical fiber, is frequency dependent. So different frequency components, which means different wavelengths of light, travel at different speeds in silica. This is called material dispersion. Material dispersion depends on the material's built-in refractive index, and we cannot change that. The second type is called waveguide dispersion. To understand waveguide dispersion, we need to know that light pulse travels partly in the core and partly in the cladding of the fiber. Light travels slower at the core and faster at the cladding. The overall speed depends on the proportion of power that is distributed in the core and cladding. However, the power distribution itself is a function of the wavelength. The longer the wavelength, the more power in the cladding. So different colors of light travels at a different speed because of different power distribution in the core and cladding. This phenomenon is called waveguide dispersion. Since we can change the fiber's refractive index profile, we can engineer the waveguide dispersion to make specialty fibers. The total chromatic dispersion is the sum of material dispersion and the waveguide dispersion. In this figure, we can see the dispersion versus wavelength curves of the material dispersion, shown as the red line, the waveguide dispersion, shown as the blue line, and the total chromatic dispersion, shown as the pink line. Even though we cannot change material dispersion since it only depends on the optical fiber material itself, we can change the fiber's refractive index profile design to make the waveguide dispersion compensate for the material dispersion. So we can get zero chromatic dispersion at a specific wavelength. As shown in this figure, the zero chromatic dispersion point is at 1300 nanometer. This picture shows the chromatic dispersion profile of a standard single-mode fiber. So there you have it. Please leave your comment below if you'd like to see other topics. Don't forget to visit foforsale.com for more free fiber optic tutorials. I will see you in the next video.